So let's talk about integrated circuits. What are the integrated circuit? Basically, just to every one of us, also these days, also when we are dealing with our laptops, we are dealing with the integrated circuit. Integrated circuit are basically circuits that are embedded on a board of silicon. Okay. What is the difference, for example, with non-integrated circuit? If you open an old radio, or even Spinardi and Igor, they are saying, if you're using a breadboard, okay, you are like have as well circuits, no? Because all the electronical devices are made by circuits. But you can put and place all the components, and the components are, we can say, not integrated into the board, but separated, and then you have to solve it, okay? Basically, when you have to solve the elements, and when everything is, we can say, soldered on the tracks and so on and so forth, that are not integrated circuit. There are basically circuits that are made by single components and so on. They become integrated when basically everything is printed, and we will see some techniques, and we will see also these techniques Monday when we are going into the ST microelectronics. There are nowadays technique based on physics, based on the we can say modern, we can say photolithography techniques and so on, that can print and create the same properties of a circuit just on a silicon board. So for the beginning, when we started, we saw resistors, we saw capacitors, we saw the LED, we saw different basic component of electronics. This component can be like a single one, like the one that we are managing now with Arduino and so on and so forth, or can be embedded into the board thanks to some properties properly of the silicon board. So just to tell you, you can hear these words are like the typical term that are used into the science of integrated circuit, because it's a science, no? It's a mix between chemistry, physics, also laser techniques, laser physics and so on and so forth. So FAT, microprocessor, digital, MPC, MOS, analog, transistor, microcontroller. These are all words that are pertaining the word of integrated circuit. I will explain some of that, but it's not the topic to explain every of these words, but just to understand what they mean. For example, NPC MOS. MOS is like a type of transistor that is like using all these elements. N stands for like nitrogen, P for phosphorus, C for carbon. Okay, MOS is like the acronym of a component that is basically I don't remember the exact acronym, but the last word is silicon. Basically, it's printed on silicon. Transistor as well. A transistor we see, for example, with Igor, is a component that is kind of a sort of a switch controlled by a third element. No, you can put the transistor 0 or 1, controlling that with a third, we can say, signal. Okay, so you have an input, an output, and a third line that is controlling the switch. It's kind of an automated switch. Okay, microcontroller. The microcontroller is, I mean, we know microcontroller in every device. In every device, there is a sort of brain of the device. Into the laptop and desktop, this is the CPU, no? The microprocessor. When it's gonna be more powerful, we call that microprocessor. But even in, I don't know, our watch, our, I don't know, printer and so on, there is a microcontroller that is basically the brain unit, no? The one that is making calculation to let the electronic device work and so on and so forth. The microcontroller can be as well separated. For example, we see in the laptop and it's in the desktop that are like unique bodies that you can print or that you can attach, sorry, or detach from the motherboard, but they can be also printed inside the motherboard itself, okay? And we'll see a little bit the technique. So, first of all the science of integrated circuits, okay, is um, working on certain type of materials that have a particular property, okay? This property is the semiconductor property. What do you think it is, a semiconductor? What is a conductor, for example, for you? Tell me a material, for example, that can be a conductor.
Copper.
Copper, exactly. Or even iron, okay? All the metals are full conductors. Basically, all the metals can let go the current, okay? The electrons go flowing among the material, okay? So these one are called conductor, full conductors. But there are some other material, and we will discover one in particularly that is used into our industry, that is properly silicon, that is not so well conductive as copper, as iron, and so on, but can conduct in a certain way. But moreover, the conductance depends on certain property. So, for example, depends on the temperature, depends on the voltage, okay, that is in the middle of the material, okay? So the semiconductor can have particular variables that are governing the conductance of the material. Okay. This, at the beginning, when electronic was born, of course, was not such a big deal. Everything was working in copper, iron. If you see, for example, the old circuits, even the battery, the Volta battery, the first battery was made by a composition of copper and iron, okay? Because that one are material that can let flow very easily the electrons, no? And so for all the electronics are very good. At the beginning of the story of electronics, semiconductors were not so popular, okay? But with the physics, with the advancement even of quantum physics and so on and so forth, this type of material has become very interesting and basically one of the base of the modern electronics, okay? Just show, as I say, one of them that is silicon. Silicon is one of the most used. No, I mean, you know the Silicon Valley. No, Silicon Valley is where all these electronics are designed, made, studied, and so on and so forth. Silicon is a type of material. Let me share my screen. Okay, that is not. I mean, copper, iron, and so on and so forth are material that we can say are made by one single type of atom. Okay, so copper is made only of atoms of copper, iron is made only of atoms of iron, and so on and so forth. Silicon, indeed, is a molecule. Okay, is a molecule that is made basically by a silicon atom, okay, and four oxygen atoms, okay. So this is the basic molecule of like silicon. In nature, basically this molecule is in form of crystals, okay. And in fact, this is an ion. I don't know, you know what is an ion, no? An ion is basically something that has an electronic charge. No? In chemistry, it has something that has an electronic charge. For example, the ion of silicon has 4 electrons missing into the global structure of the atom. That means that is very, you can say, greedy to connect with other molecules in order to fill this electric charge that is exceeding, okay? Everything in chemistry, in nature, need to be neutral, okay? So if we have 4 electrons here, this molecule is gonna combine with other molecules in order to fill these 4 electrons, no? I don't want to go too much into the chemistry, but just want to say that in nature, we find this element into crystals, okay? Crystal of silicon. And in your opinion, where you can find a lot of these crystals of silicon? Have you ever seen that? The silicon crystals?
Not really.
Are you sure?
Now you're making me guess myself. I don't know.
Now I'll tell you, and you will say, oh my God, it was so easy. Okay. So, first of all, this silicon molecule is also called silicon dioxide because it's like silicon surrounded by oxygen atoms. Okay. This is the basic composition of the sand. Okay. Sand or even the glasses are made of this matter. Okay. This is a very diffuse mineral, in one of the most diffuse mineral in the world. And the basic, I mean, where we can find a lot of these is properly into sand, okay? Sand is we can say, the different grains of sand comes from the erosion of the rocks and so on and so forth, and so can be composite in a way. But the most prominent part of the sand is made of silicon or silicon dioxide, okay? So the basic material of the silicon, like the raw material of the circuits is properly sand, okay? And we will see, and also in ST microelectronics, they will tell you. I mean, I was telling to you that was very easy. So the answer now, if you have seen the silicon dioxide or silicon, I think that for sure you have seen the sand, no? Okay, so basically, semiconductor can be used for several uses. Here, the slide is showing different uses of the semiconductor and so on and so forth. And the property of semiconductance, okay, is due to, I don't want to go too much into physics, but just to tell you, is due to the fact that the silicon molecule, okay, let's go back 1 second to the silicon molecule, and the silicon crystal, okay, is sharing into the crystal lot of electrons. Just basically this molecule to stay together, okay, is sharing a couple of electrons between one silicon to another, okay, to stay neutral, okay, is a type of bond that is called covalence bond in chemistry, okay. I will not go too much in that, just I want to tell you, okay. But the issue is that we have into this sort of you can say texture of silicon, we have a lot of electrons that are semi-binded, okay? Semi-binded because for a little bit they are attracted by the atom of silicon, for other bit are attracted by these atoms of silicon, and in the middle they are staying quite fixed, okay? Not so much, okay? If we are feeding this crystal with a certain type of energy that is gonna excite the electrons, and so they are gonna move this electron more fast, for example, we basically create a lot of electrons that are free to move, okay? And when, for example, we raise the temperature or we give a lot of potential, we give energy to this crystal is gonna start to conduct, okay, as metals, okay. I will just share you, for example, the molecular structure of metals, okay. Okay, this is an example. This is like an example on how copper is in reality, okay? Basically, the atoms of copper are in a sort of sea of electron. It's properly called sea of electron. This sea of electron, you have to imagine like a lot of negative charge that is free to float. That's why are very conductive. So that's why copper, iron, all the metals are very conductive. Because the central atom, we can say the nucleus, is immersed in a sea of electrons. And so they are very free to move and they are very free to conduct the current. That's the same situation of silicon when we give energy, okay? When we do not give energy, of course, these electrons are a little bit binded, no? So they cannot move. But indeed, if we are giving energy to all these texture, then these electrons are free to move and the silicon is starting to behave like any other metal, okay? That's why they are called semiconductor. And that's like a very big property that these materials have. But now let's go ahead. Here you see, here is the model that I want to share to you. Copper, that is a conductor, it has a sea of electrons that are free to move. And semiconductor, indeed, you have to push some energy to let a lot of electrons to transit from the so-called valence bond to the valence band, okay, to the conduction band. Let's go a little bit back here. The valence band, it means all the electrons that are linked to the atom, okay? The conduction band, it means all the electrons that are free to move, okay? So if we give energy to the electrons into the valence band, more of them can go into the conduction band. And basically we can induce, we can say increase the conductivity of the material, okay? So here, I don't want to go too much in deep on that, but just to say that these are type of circuit, the MOSFET, the N-channel MOSFET that are made properly exploiting this possibility of the silicon to push some electrons from a lower state of, say, valence to a covalence bond, okay? So, for example, imagine that the electron are the water, no? The electron are water that we need to let it flow, okay? We can create in some ways a possibility into the same material, okay, into a block of material to have a reservoir of electron that we can push and move to a channel that is, for example, the conduction channel, or eventually we can also create some gateways, okay? All these things only working on the chemistry of the surface of the silicon, okay? Remember this image of the sea of electron, okay? If we have a block, for example, a layer of silicon, we can push the electrons in different areas of the silicon to have more or less energy, okay? And in a way, working on this pushing to have more or less energy, we can create areas in which electrons are more like dense, more like able to conduct, areas where electrons cannot conduct, areas where like electrons can conduct only in a certain way. And we can start to imagine that. Imagine like that we have an entire, we could say, flat surface of silicon. Just putting some energy in different point of the silicon, we can say, plate on the silicon plane, okay, we can create areas that are more conductive. We can create areas that are less conductive, areas that are isolant, and so on and so forth. Basically, it's kind of we can print on the surface of the silicon different components, no? For example, I want an area that is more keen to let pass electron. For example, I want to create a resistance. I can put some energy in a way into that area of the silicon, okay? And I can push the electrons to go that way. I can create a channel, okay? All it is, as I said, working selectively in different areas of the say silicon strata. Can work selectively in order to create reservoirs, channels, and so on and so forth. I can basically print on the surface. Of course, when I print on the surface, I can create a circuit that is integrated into the motherboard. Okay, I cannot detach the resistance. I cannot detach the LED and so on and so forth. Everything is printed on the surface and integrated there. Of course, which advantage can have this type of techniques in your opinion? First of all, is quite clear what I'm telling to you. So I render you the idea on how we can work with the silicon in order to create circuits that are printed. Was it clear, the explanation, or was like some missing holes and so on?
Yeah, it was clear.
Okay, okay. So the concept is that silicon is a semiconductor. Silicon, we can manage the conductivity of the material in different ways. Then we will see how, okay? And basically, based on the fact that we can manage this conductivity of the material in different ways, we can print and create circuits on the surface of a sort of layer of silicon, okay? Of a crystal. The layer of silicon is basically a big crystal of silicon that is flat, okay? In your opinion, which is we can say, the advantage of have this possibility? Why I need to print circuit on silicon rather than make a circuit with single component? Which is, in your opinion, the main advantage? Why we go into this direction and we change from having a single components on and so on? I mean, print on silicon can also require a lot of industrial effort and so on and so forth. But why we decide to go in that way as, we say, technologies and so on? Any guess?
Because
Hello?
the silicon is easy to make different shapes.
Uh-huh. Different shape, and I can say also smaller shapes, okay? So on silicon, I can really act with the modern technique even to the atomic level. So if I want to create a sort of reservoir of electron, I can decide that, I don't know, 4 electrons can be the reservoir, and 4 atoms can be the reservoir, and 5 other atoms cannot be the reservoir, and so on and so forth. So I can scale basically the same circuit with the same proportion, okay, in the nano dimension that I want, okay? Basically, this work with the semiconductor has opened the way to, we can say, scale down and to create microchips, okay, using the same circuit, okay? for example, with Igor and with the people that are working with Arduino, we are going to design a circuit, okay, that is made by a LED, a resistance, and so on and so forth. The same scheme, okay, the same scheme that we did on the breadboard at the dimension of centimeters and so on and so forth, we can scale down into a microchip, okay, just using the printing techniques on silicons, okay. So basically, these invention, I mean, these techniques to manage the silicon semiconductors has led us to miniaturize the electronical devices, okay. Now we have even nanocomputers, okay. We have quantum computers and so on and so forth. That's thanks to the fact that we can manage these properties even at the atomic level, okay? So the main advantage is that basically semiconductor has opened the way to miniaturize the electronic device, okay? Okay, so this is an example of the so-called MOSFET. MOSFET is a transistor, okay? As I say, the acronym, I don't remember exactly, but is related to the process in which they are produced. Maybe when we are gonna go to the ST microelectronics, we will see. But basically, as you see from this is like the magnify image of a microscopic layer of silicon, okay? You will see here, this is the main plate, okay? That is a type of silicon that is called P-type. One thing that I didn't tell you, you have to imagine silicon as a crystal texture, okay? Into this crystal texture, you have to imagine that I have a lot of nodes, okay? But I can create, for example, more density of electrons, even if I change my node, my silicon node, with another material, okay? For example, I can put inside the different node of the texture a material that can have more or less electron available to, we can say, to go into the covalence bond, okay? Sorry, into the conduction band, sorry. So I can put like a spot where there are more electrons free, okay? This technique is called doping or drugging. It's kind of I mean, we see into the sport. Is kind of we give more energy or more we can say extra possibility to silicon to perform the function of conductance, okay? And so we can dope, okay, with like more positive holes, or we can dope even with more negative charge, okay? This difference in electronics, you know that when we have a plus and a minus charge, it's automatically creating a flow of current, okay? So basically managing the texture of my silicon, I can foster and create atomic currents, okay? That basically can render my circuit very easily, okay? And so here, this image that you can see here is properly the result of an engineering of just a silicon flat base. Okay, on the base we created an isolation oxide. So we do some treatment in order to get this area not conductive. In this area, we put more electron in a way. In this other area, less electron, and so on and so forth. Putting this texture in a different way, we create a channel that can be able to, conduct the energy. And remember what I said, what I tell to you. The conductance of the silicon can depend by the energy that we give to the material. Okay. So if we are able to give, in a way, some energy to the material, my silicon is going to conduct more or less. And for example, how we can give more energy to the material? For example, putting on the top of this material a connection to, I don't know, an electric current or some voltage that is creating we can say, an electric field that is increasing the possibility of the electron to flow and so on and so forth. Basically, okay, remember what I say to you about transistors. Transistors are kind of switch, are kind of gateways that I can control with a third signal, okay? Just with this structure, I created a transistor. So I have the channel here that is flowing normally and so on. We can say, connect this pin to an external source of energy, for example, the Arduino or whatever, the battery and so on and so forth. I can induce more energy to the system in order to put the electrons go into the conduction band. And basically, I create a channel that I control just connecting externally with a pin, okay? And look how it was so easy with the semiconductor. If I would make it work with single component this way, I should have used a lot of resistance, a lot of battery, counter batteries, and so on and so forth. With the technique of silicon, I could create transistors in a very simple way, okay? It's clear? Can you render the idea? As I said, here you have to imagine that I can work on the surface of the silicon and make a sort of channel of electron flowing, okay? Because I work into this like a different texture of the silicon crystal. Here I put an external pin that is giving energy. Giving energy, I can change the conductivity of the texture, okay? And so I can control the amount of current that is flowing here and there, okay? For example, with Igor, we saw that if we, when we are opening the strip LED, okay, we are connecting this pin to Arduino, and this pin to Arduino, when it's high, when it's giving energy, more current is flowing, okay? When it's down, less current is flowing, and the LED are not gonna, we can say, turn on. Hmm? So quite clear, no? Or not? Give me feedback, guys, because I think, I mean, this is a complex things, and maybe. Okay, I think it's a yes. So tell me, which is the basic unit into electronics, into informatics that, for example, it need to be switched on or switched off, 0 or 1. What is the single information that is need to be switched on or switched to 1? Guys?
The channel?
No. Even though this is the easiest than you think. What you study informatics, right? Basically, no? Which is the
Yes.
single unit of information? I cannot hear you.
Electrons?
No? In informatics. The bit, no? The bit need to be 0 or 1. And even in a controlled way, no? So imagine we have here this semiconductor that is called MOSFET, okay, that I can control when it's passing current 1 or when it's not passing current 0, okay? And this is, we can say, at a nanometer scale, okay? If I make the same operation on the 10 nanometers ahead, 10 nanometers backward, and nanometers forward, what I have? I have 10 bits, 10 bits on the other way, okay? If I multiply for, I don't know, 1,000, I can have, you can say, a megabyte. So just working on, for example, 1 centimeter of silicon and replicating the same structure here, for example, I can have a device, a structure that can control the 0-1 sequences, okay, very easily, just connecting some pins, and that can, for example, can store my bits information in just 1 centimeter, okay? Basically, this MOSFET has been the open road for all modern informatics to grow up, okay? At the beginning, when I think that you for sure you have studying Turing, no? The Turing machine and so on. The 0-1 were stored as like a manual switch, or eventually you can say uh, like perforated discs, okay? And so the 0-1 was managed manually even, okay? With the transistor, just with electronics, you can manage to have more 0-1 in a shorter space, okay? And you can start to store, I mean, from the mega to the giga and so on and so forth, in a exponential way. This MOSFET, that is one of the basic technology of you can say semiconductor, has opened we can say we can say an open road for informatics to grow on the level that has been today, because we can control the bytes just with electronics, okay? Here an example of a capacitor and so on. Of course, when we are talking about semiconductor device, we can have analog device, okay, analog that are working basically on the full signal, full electric signal. Digital device, as I said, the MOSFET, the one that I showed you before, we can take as a 0-1, you can say, switch, okay? And the 0-1 switch is basically storing the digital information, or even can be mixed, okay? So we can mix into the same silicon circuit some parts that are more analog, so they work on full electric signal, or some one that are more digital, okay? And so on and so forth. And now, I mean, it's opening the world and so on. But now I want to go on the techniques. These are example of complex structure. Of course, now we explain the basic technique to build the, we can say, the atomic element, for example, the transistor, okay? One single unit, okay? Building up with this unit, we can create, I mean, lot of structure, the microcontrollers that are made by bits that are registering, bits that are calculating, bits that are making the addition. There is the arithmetic logic unit, there is the RAM, there is everything and so on and so forth. But everything with the same, we can say, technology, the semiconductor technology. And I mean, you see the development of electronics that have been since the semiconductor techniques has been discovered. We go faster and faster and so on and so forth. Here's some example of mixed signal. For example, the MCU are a mixed signal because the microcontroller is working both with some full electronic signal, but also with like digital signal and so on and so forth. But now what I want to go, I mean, here there are multiple structures that you can create, and this full package, remember what I say to you, Silicon Techniques has opened the way to miniaturize. And even though this is a complex structure, I can render into few centimeters, okay? Because I can scale at even molecular level, okay? An entire circuit, an entire, you can say, gigabytes of things, okay? And so on and so forth. Here are like different other examples and so on and so forth. But let's go. I mean, when we are talking about silicon and integrated circuit technology, we are working on the level of micron. Okay, micron is basically one over 200 the width of a human hair. Okay, so we can act, as I said, so little with the modern technology that we can scale down in an impressive way, okay? Here a little bit of comparison on how much is a, we can say, nanometer. At the nano level, nano is 10 minus 9, okay? 10 minus 9 meter, and so on and so forth. But what we are going to see, for example, when you're going to go to the ST microelectronics, we are going to see some manufacturing processes of the integrated circuits. Okay, so how is possible to realize all the things that I say to you before? Okay, we start from sand, as I said. The sand, usually we can heat it up, okay, and we can basically let join all the small crystals of silicon into bigger crystals, and so we can create silicon, okay. When we like heat it up again and in a controlled way, we can create ingots, okay? And for example, we can cut transversally the ingots to obtain the so-called wafers, okay? What we are gonna see into ST microelectronics will be wafers of silicon that we can print, okay? These wafers are basically the substrate on which we can print all the things and so on and so forth. Then we can use some dyes, we can package, and then we obtain a chip. Okay, so this is the full process of manufacturing of integrated circuits from sand, as I say to you, to chips. Okay, and when we are going on Monday to the ST microelectronics, we will see properly this process here. Okay. And so there are different fundamental process that in which we can print over the silicon wafer. There is the diffusion. So for example, grow or deposit of a layer of oxide, nitrate, poly or similar material. I told you, no, if I have this surface that I can manage, I can basically create poles, I can create isolation areas, I can create etches, I can create channels, and so on and so forth, just working even on putting on the top other type of material that can change the property of my texture, okay? There is the photolithography. That's what we are gonna see, for example, when we are gonna design on KiCad, okay? On KiCad, we are rendering the circuit as basic elements, okay? Then the program automatically is gonna create the counter image of the photolithography. And then, for example, if we send these to We Do Lab, as they told us they're gonna do, basically they photo modify the surface of the waffle in order to print the image, the tracks that we say to them. Okay, so we can give the negative, and they can print the photo of our circuit directly on the wafer of silicon. So we can etch, so we can remove some part, we can implant dopants. As I say to you, if I change the holes, the nodes of the texture, I can also increase or decrease some properties of my texture. And so I can create areas with more electrons, areas of less electrons, and so on and so forth. I can put metals and films areas. For example, if I want that an area is super conductive or more conductive than the rest, I can just deposit on the top a layer of metal and so on and so forth. So I can do a lot of things. And in ST microelectronics, they are doing properly this operation, okay? Which is the pipeline, okay? We have the buffer, we create the mask. First, there is like an epitax, so the buffer surface is clean by all the impurities that they can have. These operation that we're gonna see, they are made in the so-called white chamber. White chamber is a ultra clean environment because you have to imagine if you are working at the nanometric level, like with the atoms, any little dust, any little impurity, and so on, can damage the process. Okay, so the areas where these chips are gonna be manufactured, basically are super clean. They have an extra vacuum. They have always a flow of air that is changing the air, and so on and so forth. And as you have seen, for sure, the people that are working into this environment, they wear an entire suit, basically to do not contaminate the buffers and the chips with I don't know, their skins, pieces or impurities on any genre. Then there is, as I said, after the cleaning, there is the photoresist, then the photolithography. So basically, photoresist is to put a layer of, you can say, non-conductive material in order to like put everything on the same level of conductivity. Then there is photolithography. For example, when I put the photoresist, I can I can take out selectively the part that is more resistant in order to create channels, in order to create bus, and so on and so forth. When you see, for example, into the motherboards, that there are the areas that are more, you can say, copperhead and so on and so forth. These areas are properly realized by this system of photoresist first, and then I take out the resistance that I don't need to create a channel by the photolithography process and so on. Then there's the etch, the stripping, and we will see most of them also when we are gonna go there, and so on and so forth. As I say, this way is also created this structure by changing the properties of the surface and so on and so forth. And everything is starting from the silicon, no? The industrially silicon is melted, is putting in temperature in order to create these ingots. Ingots, then they are cut down in waffles, okay? They usually the way on these are cut is by laser, okay? Because they need to be very precise, and the thickness of these kind of wafers are of 640 microns, so 10 minus 6, okay? And then we can build up all the things. You see, this is an example, no? Substrate with thin film, then we can put a resist coat. We can make the photolithography, so we can take out selectively some part of the resist. Then we can put something more, then we can etch, we can do a lot of things, okay? This is the process, no? In a nutshell on what I was telling to you. We have the buffer that we can put a photoresist on the top. The photoresist is gonna create the base for create the tracks. Then with the laser and lens, I can selectively remove the photoresist, okay? Photoresist is gonna basically isolate the upper part of the buffer, okay? Also because if I expose to the air, my silicon do not be damaged by the contact with the oxygen and so on and so forth. I can etch, I can put some metal conduction and so on and so forth. And this way, this process is properly the way on how any circuit that we are dealing with nowadays is made, okay? And so on and so forth. So I will leave this slide to you. Now I'm not going too much in deep. Here there are the explanation of all the different processes from the etching to the diffusion to the ion implantation are chemical processes that are used basically to condition the surface in the way that we like most. Okay, we can create layers. This is the basic buffer, and these are layers of material that we can put on top, and these layers are gonna create resistance, diode, whatever. Okay, and that's it. I don't know if there are questions or comments or curiosities even, huh? Are you alive? I killed you.
Yes, right.
Yes, we are.
Yeah. Okay.
Don't worry.
So tell me also what you think. I mean, if you did know this before, if you have some curiosities, was useful, was meaningful. I don't know.
It's different for sure. I never seen like how fundamentals work like in microchips, and it's also good so when we get on microtransistors Monday, we are not uh, on the blank.
Yeah, I mean, I think that, for example, when I discovered these techniques, I mean, I studied this technique in university and so on and so forth. But then I render, for example, how the RAM is working, how the different even board are working, and so on and so forth. And really the concept is to arrive to the bytes, to arrive to the gigabytes, to the registries, and so on and so forth. Everything nowadays is based on these basic units that now are nanometer scale. Okay, and think about that. You can easily imagine how, for example, nowadays we can have a smartphone that is kind of a laptop of 10 years ago in just our hands. Okay, or even I don't know, even Arduino. It has the power of the first PCs. Okay, gradually the study of semiconductor has allowed informatics and electronics to really make big advancement steps in order to create more and more complex devices. Okay, you have to imagine our cells, they are like sort of chips at the nanoscale. So that's why, for example, nowadays we have also artificial intelligence, no? Because we have been able to reach such a small scale that just multiply the same technique, we can arrive to, I mean, the number of millions of cells, for example, that we can have in our brain, for example, no? Nature is even more refined into this, we can say, way to miniaturize. I mean, every of our biology process, they are working at the nanoscale, at the atomic scale. Okay, the silicon techniques has allowed us, of course, not to arrive at such a level. It's still not that. Even though now I show you one thing that can be interesting. Nowadays, there are also studies that are using biosensors. Okay, biosensors are basically chips that are integrating biological structures into the silicon. No, for example, the I was called the sensor of humidity that now for you Igor and Spinardi you are doing and so on and so forth. Sometimes can be also a biosensor. Okay, let me show you one possibility of this kind of technology here. This is like a liquid calorimeter. Okay, basically this liquid calorimeter is measuring the heat produced, for example, in a flow, and also some other chemical properties, creating a microcavity into the sensor. This is a nanometer scale, okay? A microcavity into the sensor that is sensing the difference of heat between two membranes, okay? And on this membrane, there are also some biological enzymes that they change their shape and produce some electronic current, okay? When there is, for example, a certain pH or whatever, okay? So in scale of a nanometer, you can create the same operation that you are performing into a lab, for example. No, if you want to measure the pH or you want to measure the heat inside, I don't know, a fluid or whatever. In the past, we did with I don't know the mercury bulbs or the pH indicators and so on. You have a lot of tools and chemistry things to do that. Nowadays, with just working on silicon, because you see, let me go a little bit more in zoom. This structure here is nothing that a wafer that is, of course, manufactured in different ways. And this is the same, is starting from the same wafer that I showed you before, okay? And we can do a lot of, say, sensor. Of course, here are these are all the, say, technology behind and so on and so forth. But everything nowadays can be miniaturized at the nanoscale with the semiconductor technologies and so on and so forth. Okay. So, any questions, comments?
Not really.
Okay, if no, just one thing regarding you know that we have this project of for the lake, no? I'm just asking if Tomas or anybody of you has a little bit go ahead with that. Even I mean, completing a little bit the task that we did last time. So just to tell, I mean, I don't want to. Does anybody of you has given a look to the project there and has some updates?
For me, no.
Okay. So maybe Thomas, if you can, because I reach out to Mercedes, and maybe I mean she need to confirm. Maybe on Saturday 5 we can have a jump there. I mean we will not stay long, but we can have a jump there on Saturday 5 to at least give back the solution that we were thinking to them for them. So maybe for 5/8, at least we can finalize the document that we started last time and give them as a suggestion and so on. Of course, they can then take their decision and so on and so forth. But for the yeah, tell me, Igor.
What?
I was saying that
Sorry?
let's remember that that project that we had with the lake. That maybe on the Saturday 5 we can have a jump there and just give back the suggestions that we organized. The file that I shared with you last time. I share again maybe into the chat.
On what day? Sorry, I didn't get it.
On Saturday 5 July.
Oh, 5 of July, okay.
Yeah. As I say, I reaching out to Mercedes and maybe we can remember that we have to go the previous Saturday, but there was no chance. So maybe we can go back on the 5. So let me share. One also other interesting news, if I mean, that I want to share with you. So I was asking before, guys, the exact day when you are gonna basically leave from Italy. You say that the last day is 8, right? Correct?
Yes.
Okay. I was asking that because maybe as final moment of our experience, because I think that it's important for you, and I think it's not so common to have it. Here in Milan, there is an headquarter of European Parliament, okay? So a communication office of European Parliament. Now we get into a lot of technical issues, electronics, informatics, and so on and so forth. But I think that first of all, you are making an Erasmus project, okay? An Erasmus project is a European project that is helping us to really like be European citizens, okay? And so now I call upon the headquarter because there is a friend of mine there that is working. If there is the possibility to give you a greet, okay, so to go there and to let you show let them you show let them you see, sorry, um, the headquarter of the European Parliament, no? It will be not like anything's technical, but it will be like basically the home of our project, no? Because Erasmus is an European project. That quarter is located near Cadorna. I don't know if you remember. No, you know Cadorna, no?
Yeah,
Yes.
we know.
Yeah, yeah. And so I'm organizing an official visit to the European Parliament headquarters there. I will let you know because they suggest me to be that this visit can be on the 2 and will not last more than 1 hour and 2 or 2 hours. So in the morning, maybe. Um, or eventually on the 7th. Okay. But I'll let you know. But I was thinking that maybe as a final experience of your path here, that could be nice to have also a little bit of knowledge of the European Parliament. What do you think?
Yeah, it will be a
Okay.
great idea.
Okay. So for now, that's it on my side. So as I say, today, unfortunately, due to my, we can say, decomposing arm that is gonna detach, yeah, we cannot, we cannot go to Gigi's.
Lego
But
arm.
sorry,
Detached.
sorry,
I said it's a Lego arm. It
it's a
detached.
Lego arm, exactly. So today I'm gonna repair my arm and all the devices. And so see you tomorrow. Okay.
Okay.
Good.
Bye.
Thank you. Bye bye. Bye bye.
Bye, Domenico.
Ciao.
Bye bye.
Bye bye.